it helps us to figure out how to run NLMixR and some of the things that can be done in it. First thing that I'll run is the knitting options and the way to cache the NLMixR fits. Then if you recall, the way to add covariances between subject variabilities is this little pseudo type of language where you add the between subject variabilities together and then have a tilde that tells you this is going to be modeled by a lower triangular matrix. So let's start by loading NLMixR and in particular loading the Phenobarbitol data. So first we have this Phenobarbitol data that was loaded, and we're going to create a Phenobarbitol model. We have the clearance that we have typical value here. If you look here, it's on a log scale, which means down lower, it'll be on a log normal scale here. Same thing with the volume. And then we have this eta of clearance plus eta of V, and then we'll have the lower triangular matrix of this estimate. We'll also assume additive error with this residual variability. And then we put the relationship between the typical and the between subject variabilities and the actual parameter here. So for example, clearance would be the exponential of the typical value plus the between subject clearance deviation, or eta. And we have our volume, which is also log normally distributed. And we have our elimination, which is our clearance divided by volume. And then we have our central compartment. In this case, we call it A1, which is something that people say amount in the compartment 1. We say that the elimination is KE times A1. And then our central compartment concentration in the plasma, or CP, is equal to our amount in compartment 1 divided by our volume. And this CP is going to be modeled by an additive expression. So we evaluate this model, then we fit it with SAEM. Here we can see the objective function, it seems reasonable. And we can see the parameter estimates. And here we have the estimate and the back transform value. You can see negative, it makes a small clearance value. And then we have a typical value for the volume and the additive error. We also have the confidence bands and the CP percentage that we can go through and look at. When we look at the omega piece, we can see that there's a correlation between these two etas. And in fact, if we look at omega R, we see that the correlation is quite high. It's 0.98. And this is consistent with the idea that clearance and volume are often correlated. I also have the shrinkage distributions, the notes about the fit, and the data itself. NLMixR fits are data, so you can use them to do plots or data manipulations. So first thing we'll do here is just get some basic goodness of fit plots. As the standard things, you can see them in small. There's the trace plot, these DV versus pred, residual types of plots. And at the bottom, you can see these individual plots. These individual plots are fine. I would like to really see what's happening with the dosing and the concentrations. So one way to do that is a function in NLMixR called augpred. It is inherited from the NLMe augpred. What you do is you take the augmented prediction of fit, it'll return a data frame. But if you plot it, you'll get an augmented ipred versus pred for each individual, or basically individual fits. You can see the difference just in this right here. We have 49, you don't see very much here, but in here we see patient 49 has a lot of dosing that goes up, and then eventually has this one compartment off behavior. You can see that with all the other patients as well. So you actually get a lot more information about what's happening by looking at these individual augmented predictions that you can use in NLMixR. Last thing we might want to do is this visual predictive check. So there's two different types of visual predictive checks that are common. One is a standard visual predictive check, and then there's also a prediction corrected visual predictive check. Right here, this pred core equal to true is the difference you need to have a visual corrected VPC. And then if you want to stack these two ggplots on top of each other, you can use patchwork and use a plot1 divided by plot2 type of syntax, and then you'll get both plots here. So you see the concentrations here versus time on the standard VPC. Everything seems to be okay. And you can see the predicted corrected concentrations, which corrects for the predictions. And this one shows a slightly better fit for the data that we have.